Hi everyone, this is Mrs. Leong, and I will be teaching lesson 214, logarithmic function context and data modeling. All right, so I'm actually going to start on the flip math portion of this lesson, so flip to this page, please. And I'm going to show you guys how to do a logarithmic regression, and also to know when to do a logarithmic regression. All right, so just remember that logarithmic functions have independent values, meaning the x values increase proportionally, while your dependent values, your y's, increase at a constant rate. So this will have a common ratio, where this one will have a common difference. All right, so this one you see is going up by a factor of 3, and this one is going up by a constant of 2. So this is how we can recognize that this is a logarithmic function, okay? The amount the proportional values increase will be the base of your log. So since this is going up by 3's, this one would have a base of 3. Okay, here's a note though, on the calculator, you only have a natural log base for this one. So calculator does only a natural log base for the 4 log regressions. Okay. All right, so just know that the TI-84 only uses a base E, or natural log. All right, so let's go ahead and play around with this. So example 1, at the end of the school year, the classroom gets really warm. As the number of students increase, so does the temperature. So here's some data Mr. Bean took last May. What's a regression equation to model the situation? All right, so at this point, we might not know it's a log regression, so we would look and see how this is changing. And we see that this is being doubled. Our x is doubling, as our y's is increasing by 2. So because this is proportional, and because this one is growing at a constant rate, we know that this is going to be a log regression. Okay. So let's go ahead and find that regression using our calculators. So here, let's go ahead and plug in our data. Let's go stat edit, and we're going to type in our list for 8, 16. All right, and then our next one, this one's going to be 67, 69, 71, and 73. Okay, and now we're going to go to stat, move over to calc, and we're going to go find our log regression. So there it is, number 9. We have our linear regression. All right, we got L1, we got L2 over there. To store, let me go ahead and store this in here in case I need it. So let's store that with Y1, and there's our regression. All right. So as you can see, this one has just your natural log. A is 65, and our coefficient of that, B, is 2.885. All right, so let me transfer this over back to my notes. So this is our function, 65 plus 2.885 ln of x. All right. And the next part, according to the model, was the temperature if there are 35 students. All right, so that's my x variable. So I'm going to go ahead and plug in 35 into my function. And since I stored this already, I can go ahead and access that. Y1, alpha, Y1, parentheses 35. Oops, sorry. Not used to this calculator. Oh, it wants to graph. Okay, there we go. 75.259 degrees. All right, So this will be 75.259 degrees. And make sure you put units, especially if it's a word problem. This lesson is all about context, so having those units helps with that context. All right, now according to the model, how many students are there when the temperature reaches 85 degrees? So that means our y, our independent variable, is 85 degrees. All right, so let's set that up. We got 85 set equal to that. And different ways you do it. You can do it algebraically, or if you have a graphing calculator, you can definitely just graph the function and see where it intersects the graph y is equal to 85. Since my calculator is not playing nice, I will just go ahead and do this algebraically. All right, I'll divide. All right, and to get rid of the ln, you can go ahead and rewrite that in exponential form. So we know that this is log base e of x. So that means x is going to be e to the power of that fraction. All right, if you type that in, that ends up being about 1,025 students. Okay. Awesome. So go ahead and why don't you try it with example 2. So pause the video, and once you're done, unpause it, and you can check your answers. All right, here is the answer for example 2. This was the model that I got using my calculator, and by plugging 70 into that, I got 19.020 minutes. Again, double check, make sure you have those units. Okay. Continuing, example 3. People measure loudness in terms of decibels using the following function, where d of I is the decibel level, I is the intensity of the sound, and 10 to the negative 12 is the intensity of the quietest sound a human can hear. What is the intensity of the sound of a school fire alarm if it registers at 100 decibels? All right, so 100 decibels, this is our d. So basically they want you to find I when d is 100. All right, so let's just plug it in. Oops, that's an I over 10 to the negative 12. All right, let's isolate the log, divide both sides by 10. Let's get that into exponential form. So this is base 10. So 10 to the 10th is equal to that. And then let's multiply both sides by 10 to the negative 12. So 10 to the 10th times 10 to the negative 12. Same base, so add those decimals, or excuse me, add those exponents, and you get 10 to the negative 2, so 0.01. So that's a 0.01 intensity, which doesn't sound very intense. I feel like our fire alarms are a lot louder than that seems. All right, why don't you go ahead and try example 4. So pause the video, and once you're done, unpause, and you can check. Okay, so the answer for number 4 for Mr. Brust to get a new Lamborghini is 14.9%. If you left it as a decimal, that's totally fine, but usually interest rates are in percents. Okay. Awesome. Let's go ahead and go back to the first 2 pages. Here we go. And we're going to talk about these models. All right. And so we know from a table how we can tell if it's logarithmic, right? If the x variables are increasing or changing proportionally, where the y variable is changing constantly. Graphically, it would look something like that. So that's your log graph. All right, just here's some examples in real life where logarithmic functions are actually more appropriate than other sorts of function. So this one is talking about salaries, average salary for a church pastor as the church size increases. So as you can see, as the church is increasing, the salary goes up, but then it kind of slows down as the congregation grows, okay? Other real world scenarios would be like, measuring earthquakes, sound, acidity, All right, so those are just some examples in the real world where logarithmic functions are useful. Okay, so yeah, we already talked about this, about how you can see from a table, or you can see the x and y changing, how they change. And you can have a natural log, you can have, common log, any log base, but that is the general function model you will have. All right, so let's go ahead and try a situation where you know 2 data points and you want to write the actual function based off of those 2 data points. Okay, so example 1, and I remember actually seeing this very, very similar question on an actual AP test recently. So yeah. Select values of the log functions are given where they give you the basic form of that or the general form of that. Use the given data to write 2 equations that can be used to find the values for constant b and c in the expression for L of x. All right, so for the first part, they just want you to write the equation. So just plug in your x, plug in your y. All right, so for the first point, 2, 3, you can just plug in your L of 2, or you don't even need that. You just plug in 2 into your general function, set that equal to 3. And then for the 0.57, plug in 5, and you get 7. All right, so those are your 2 equations. Done. All right, part B, find the values of A and B. So hopefully you're looking at it like this, and I wrote it like this on purpose because it's supposed to look like a system. So let's go ahead and set up that system. I'll just copy and paste this down. Set up a system and solve for A and B. Paste, there it is. So the A's look like they are easy to eliminate. So let's go ahead and subtract those. So you get B of ln of 2 minus B ln of 5 is equal to -4. All right, to solve for B, let's go ahead and factor out the B and then divide both sides by that ln of 2 minus ln of 5. All right, and that ends up giving me 4.3654 ... once I plug that into my calculator. All right, so going back up here, so this is 4.365, and then just substitute that back into whichever one you want. Let's plug it in here, and then you can solve for A. So A is going to be 3 minus 4.365 ... ln of 2. A ends up being -0.026. All right, so plug those in, set up a system, and solve for A and B. All right. So let me see, example 2, we kind of already did. Similarly, we're just going to plug those in and get your regression using your calculator. So we'll go ahead and skip that one since we've done a few of those already. Okay, example 3. This one, again, very similar. Let me have you guys go ahead and practice that for homework. And actually, yeah, I think that's it. So go ahead and let's have you try this. Actually, let's try this now. See if you got it. Find values for A and B. So pause the video, and once you're done, unpause, and you can check your answer. All right, so here is the answer for example 3. We got these 2 equations when you plug in the information into the function they gave you. And if you were to solve for A and B, you should get 120 for A, 10 for B, and that's my work over there. And then for part C, substituting those all in, we got 160 decibels. All right, that is it. Go ahead and finish those packets for homework, and good luck.